We now define the potential drop over a segment of wire and explain the conventions that we use. For this, we need a direction chosen on the wire. Let's remember that for expressing the current on the wire, we also needed a direction. So for defining the potential drop, we are going to use the same direction. Right? In that case, I'm assuming that I'm walking over the wire in the direction shown by this arrow. So as a result, in this special case, of course, my initial point is at A, final point is at B. Right? I'm therefore starting my motion from the initial point and moving along the arrow and then reaching to the final point. In that case, potential change in the electric potential is change is a well-defined quantity. It's always final minus the initial. So the potential change is defined as final minus initial. So therefore, this is VB minus VA or VBA. Okay. Potential drop, however, is the opposite of this. So I'm going to show this by the symbol V drop. It is the negative of the change in the potential. So therefore, this is VA minus VB. Right? Why do we define it like that, and why do we call it as a drop? So the main convention in here is that when you move from A to B, from initial point to the final point, if the potential really drops, then this quantity, potential drop quantity, has to be positive. Okay, so if initial bigger than the final, in that case, potential drops and the amount of the potential drop is therefore positive. That's the convention that we are using it. So therefore, for this reason, potential drop is initial minus the final potential. Okay. Why do we define a different quantity called potential drop in here? The reason is that for at least for resistors, basically passive wires, we will find that the potential drop is positive if the current is positive. So let's see it like this. For simple resistors, if the current appears to be positive, then the potential drop is also positive. We can also understand why, right? So let's consider the situation where the potential drop is positive. So the direction is like that. So V drop is positive. That means that A is at a higher potential than B. Okay. So which means, of course, there's an electric field from A to B, in which case a positively charged charge carrier at point A will be forced along the direction of the electric field. So it's going to therefore move along that direction. And on the contrary, a negatively charged particle, perhaps at B, would be forced in the opposite direction. So therefore, they are going to move in the leftward direction. So positively charged particles move in the rightward direction. And so therefore, they carry more positive charges from A to B. So that means the current along that direction is positive. Right? So this would then imply that the current is positive. And the result does not change if the charges are negative. So in that case, the negative charges will move in the opposite direction, but that implies that they are going to carry negative charges to the left, which is equivalent to saying that the current is positive to the right. So we again reach to the same conclusion. So therefore, the potential drop and the current, at least for resistors, have the same sign. So from now on, I'm going to eliminate this subscript drop, and I'm just going to write V for the potential drop symbol. Okay. So therefore, the potential drop is positive if the current is positive, and so on. We also, again, for these simple wires, we also can easily see that if the potential difference is zero, potential drop is zero, there should be no current because there should be no electric field in here. And I can still say the same thing for the opposite direction. So that means if the potential drop in this given direction is negative, this means that if I choose a axis or the direction in the opposite direction, and if I start measure everything, the current and the potential drop along that direction, in that case, these are going to be positive. Right? So that means the potential drop would be positive, in which case the current is positive. So therefore the conclusion that in a given direction potential drop is negative is consistent with the current being negative. Again, let's repeat that this is for resistors only, for passive elements. If there are something else in here, like a battery or an electric engine, for example, it might be possible that the potential drop and the current have different signs, but for resistors they should have the same sign. Okay, so then let's consider the potential drop versus current relation over a wire. Again, we choose a direction and measure both current and the potential drop by using the same direction. So I'm going to place the current in the horizontal axis and the potential drop on the vertical axis. So we know that both of them, when one of them is zero, the other one is also zero. And when one of them is positive, the other one is also positive. And so on. If one of them is negative, the other one is negative. So if I connect all the load values, I'm going to obtain some kind of a curve in here. So that gives us the potential drop versus the current relationship. Now it appears that this is usually a curved graph like that, but there's some kind of a region in here. So specifically this region in here, right? This is called a linear region, where for these kind of values of the current and the potential difference, they are proportional to each other. So V is proportional to the current. Okay. In that case, of course, we say that we are in the ohmic regime. We just write down this relationship as a simple proportionality relationship. So R is the coefficient of proportionality. We just call R as the resistance. And we call this law that expresses the potential drop to the current flowing as the Ohm's law. Just keep in mind that this is just an approximate law. In general, for all resistors, there are some sufficiently high values of the current such that this potential drop somehow deviates from this linear relationship. And of course, we know some circuit elements where even for small currents this can happen, so the diodes and the transistors and so on behave in a non-ohmic way. Okay. There's also a microscopic way of expressing the Ohm's law. So that's the microscopic form of Ohm's law. This essentially expresses the electric field as in terms of the current density. So it just relates the electric field, which is as a function of the current density. So you can think of this as an analog of the macroscopic form. In the case of macroscopic form, we are relating the potential drop to the current. So somehow the potential drop is related with the electric field and the current is related with the current density. We know the relationship between these two concepts. So we know that the potential drop is a constant times the current for the linear regime. And so therefore for in this linear regime, we also expect a linear relationship between the electric field and the current density. We can understand it also from this phenomenological point of view. So we are inside a wire, let's say, and then there's an electric field inside the wire. So let's just consider a charge carrier within that wire. So the motion of that charge carrier does not depend on the geometry of the wire, right? It doesn't depend on the size of the wire and the potential drop or the total current and so on. This charge carrier only feels the electric field at the location it is. So therefore, the mechanical behavior of that charge carrier depends only on that electric field. So if you remember, we have talked about the acceleration and the collisions of these charge carriers. We have said that at the end, of course, these charge carriers appear to drift along the electric field. So especially the positive charge carriers, they are going to have a drift velocity, which is actually an average velocity, which is parallel to the electric field. So for positive charge carriers, there is a drift velocity parallel to the electric field. So therefore, for positive charge carriers, the corresponding current density, which is given by this relationship, where we multiply the number density of the charge carriers with the charge of the charge carriers, and then also the drift velocity. You can easily see that for that special case, if I consider the effect of all possible charge carriers, the drift velocity would be towards right as well. So as a result, the current density should be parallel to the electric field. Okay. So the current density is parallel to the electric field. What happens if there are negative charge carriers? So there's a negative charge carrier. So I'm going to draw the electric field also in the same direction. So I'm considering the same situation. Okay, but now we have a negative charge carrier. We have said that the electric force on the negative charge carriers is in the opposite direction. So therefore, they are going to drift in the backward direction. So the drift velocity for negative carriers are in the backward direction. But again, the current density is N times Q times Vd. Right? This is the same formula, but this time let me just put primes in here so that we distinguish them from the positive charge carriers. So the negative charge carriers might have different densities. They definitely have a different charge and therefore different drift velocity. But since the charge is negative and the drift velocity is towards left, their product is towards right. So in that case too, the current density would be parallel to the electric field. So therefore, it doesn't matter what the sign of the charge carriers is. If there is an electric field in a direction, then the current density would also be in the same direction as the electric field. Okay, so this establishes the relationship between the current density and the electric field. I said that they have to be in parallel to the macroscopic form of the Ohm's law. They have to be linearly proportional to them, to each other. So therefore, we just write this relationship in this form that the electric field is equal to some number multiplied with the current density. That number has to be positive because both vectors should be in the same direction. It's just a constant, so therefore the electric field is directly proportional to the current density. Okay, so you usually see this relationship written in the opposite way. where current density is some constant multiplied with the electric field. But to establish this parallelism between the macroscopic form and the microscopic form, right, these two relationships, we are going to write it down like that. So in the macroscopic form, of course, we have a relationship between the scalars, and the coefficient is also a scalar. In the microscopic form, we have a relationship between the vector quantities, this local electric field and the local current density, and the coefficient is also a scalar. So rho is called the resistivity. We can easily find the relationship between the resistivity and resistance, at least for some simple cases. So we consider a wire with a length L, cross-sectional area A, and so the question is, if the resistivity is rho, then what is the resistance? This is quite simple to find. So we know that the electric field is equal to resistivity times the current density. That's the relationship between the vector quantities, but also the same relationship is valid for their magnitudes. So I'm just going to write down the relationship for magnitudes. So I know that the potential drop between the ends, so let me choose a direction in here. So as a result, the potential drop is the potential difference between the left end and the right end. So assuming that everything is uniform, this potential difference is equal to E times the length of the wire. So that's length multiplied with resistivity times the current density. And the current density is just the current divided by the area. Okay, so therefore, this is R times I, and so therefore R must be the coefficient of proportionality in here. So it's the length multiplied with resistivity divided by the area.